Okay, nice. All right. Thank you everyone for joining this fifth. Actually, this is the sixth session, but this is the fifth class, and we have started. We're at the beginning of the end of the course, basically. We're building the product or the projects that we are going to take to, like, you're going to use to maybe secure your job opportunities and your open source contribution project. I have some intentions towards this project. I think I might actually launch it as an actual product. So I'm just trying to make some arrangements to make it very smooth. But let's see how that goes. Um, the thing about open source codes is that you can always do something they call a fork of an open source. So a fork is when you clone a repo of something and then you make your modifications on it and you deploy it as your own. So technically, this project is open source, not even technically, it is open source because it will never be private. So any of you can clone this project and modify it to any way that you choose and deploy it as your own. I published the project under a standard MIT license, so it allows for some recreation of to some degree. So you can recreate it, you can use it as your own. I'm saying that again for the third time. You can use it again as your own. I won't come after you. No one's gonna come after you. Yeah, okay? So let me get the ball rolling. First thing first, I'm gonna share my screen. Desktop 2. Boom. So this would be the third time I am doing a review on this. It's important that I do this thing well so that when we get to the code, which is kind of like what we have started here, you begin to understand why for everything. And in the last call that we had, Ibrahim was here. He requested that we, understand why we do certain things. So I kind of added in some of that in here, even though it's largely summarized because the AI that I used to summarize it apparently was giving instructions to summarize stuff. It should not have been that brief, but I think brief is good because you guys are busy. Yeah, so first thing first, if you go on the Tattoo community, you would see this page was shared. So you can go through it at your own time. But I'm just going to try to just breeze through it and then we'll go to the code and I'll talk through the code. So, as you know, we're building a lending application and we're facilitating decentralized lending. So, the lending is coming from people like you and the borrowing is coming from people like you and I. And obviously, we've talked previously about how you will be lending into pools of different risk categories. So there's a low risk to a high risk pool, and within the time that you lend to a pool, you actually get to earn interest based on what the borrowers pay, and then some more than that. But I'll get to that. Um, Automated accruals. Yeah. So this basically says that when you deposit, your earnings are being tracked, and once they accrue to you, you can actually claim them. So we use a very interesting way of doing this, even though the accrual is going to be the most interesting bit in the code that in the videos I'm going to release after this, which hopefully will be released this week as well. Um, the accrual is not currently hasn't been written, but it will be one of the first things that we actually write because it's the most I would say it's the most important bit of the lending part. Very, very important. Collateralized borrowing, this is straightforward, nothing serious. Basically, you want to borrow assets B, you deposit asset A, and then you can borrow up to a value of asset A. That's nothing. Everyone understands. I mean, I think people understand what that is. But maybe I should use an example. Um, you want to borrow Ethereum, you want to borrow USDC, but you have Ethereum, and you have one Ethereum. One Ethereum is about 4,400. So you deposit it, and let's assume we allow you a loan to value ratio of 50%. It means you can borrow 50% of 4,400, which is 2,200. Quick maths. So, continuous interest. Yes, borrowed funds accrue until repayment. Yes. Previously we talked about using Taylor series for this. I'm thinking about it. I might not. I don't know. Depends. Um, efficient liquidations. Now, the liquidations here are going to be handled by a separate service, but the cool thing about liquidations is I mentioned that as a lender, when you lend, and people repay interest, the value of of your lending shares actually grow, so that means you can actually claim more than you deposited. But not only that, when a loan goes bad and the loan gets sold off, 40% of that loan also gets deposited in that pool. That means you also benefit when the loan goes bad, so which is a win-win for everybody. It incentivizes the lenders to provide capital, it incentivizes the borrowers to not allow their loans go bad. Because if they go bad, it's a lot of money to be made for the lender, so we'll use that to attract, in quotes, people to the platform, hypothetically. So let's look at lenders. Yeah. So the lenders supply USDT. USDT is a stable coin. I think I've touched on that before. We're using USDT because it supports 18 decimal places. Now, I should probably say it supports 18 decimal places on some blockchains. On some other blockchains, it supports 6 decimal places. Honestly, I do not know why. But hopefully the chain that we use will be one. I haven't decided on which one yet. Will be one that maybe uses 18. And if it doesn't use 18, I have a library that can convert an 18 decimal place to a 6 decimal place. No problem at all. So the lender can take three actions. They can deposit their stable coins, and then when they deposit their stable coins, oh yeah, I should probably also mention um, there is a contract that we are going to be inheriting. It's called an ERC 4626. I sort of imported it in here. And what that contract does, you can find it here. This is basically like some notes on the contract. Obviously, this is not addressing how you use it. It's just addressing a vulnerability of the smart contract. But it's not that important for this course. We can look into that after we're done building. At the moment, the ERC 4626, what you need to know is it mints shares. A share is like a token. It means shares that are based on the quantity of a pool that you hold. I'll give you an instance. So maybe Ibrahim decides to be the first person to join this pool, and Ibrahim deposits $1,000. At that time, Ibrahim is the sole person in the pool. So Ibrahim's share of the pool is 100%. So what do we mean to Ibrahim? We mean 1,000 shares because he's thousand. So we mean like a 100 shares, sorry, to him because his shares account for 100%. Now, maybe someone else comes and they provide another amount, which is 1,000. So we do, okay, 1,000 divided by 1,000, that's 50%. So we provide 50% of shares. Now, I think I might be messing that up, but I'm going to verify that because I'm actually looking up this ERC 4626 at the time of this video. I've never used it before, and I'm going to try and use this feature. So basically, it allows you to mint shares based on proportion that you already hold of the pool. So the idea being that if you own 50% of the pool, and the shares of the pool go up by, let's say 1.5%, then your 50% has benefited from that growth. So you can claim that a proportion of 50% of the growth. So this allows us to separate the assets which we are supplying versus the I would say the actual loan book. So think of it this way. You're a bank, and on your books, cash is an asset. But another thing that is an asset is also loans. Why? Because you can sell your loans to another bank and they can buy them. You know, the loans to a bank are not a liability. The loans to the person who borrows is the liability. So the total asset is cash plus loans. So this allows us to be able to track. For instance, somebody deposits $1,000, another person deposits $1,000, but 500 has become a loan. So if you look into the pool, you only see 1,500. But the truth is, the total asset that the contract actually supports is 1,500 plus the 500 as a loan. So this allows us to be able to track like what's going on when the funds are not within the contract. So that's why we use these shares. Um, Also, we allow the lenders to be able to claim earnings. Like I mentioned, when the interest gains, and the interest can gain when there's a repayment. And I think I'm going to maybe dive deep into that a little bit towards the end. The interest gains when there's a repayment, and once once we see so we have a global value. I, I'll just talk about it right now. So this is how we track the gains in interest. Now, in this model, there are non-negative gains. What that means is all the gains are greater than zero. So it might be a small gain, which is 0.0001, or it might be a massive gain of like, let's say 50, but there will never be a negative gain. So we have a value that each market has. It's something called just think about it as an accrual value. The idea behind the accrual is that if at some time the pool has maybe $1,000 in it and a person repays their loan, and the loan adds an additional maybe $1,000, the loan adds an additional 500 to the pool. The total amount within the pool now is 1,500 plus 1,500, which is 500 is, the person's principal plus repayment. So it means that the pool at one time initially was maybe 1,000, but now the pool size, actually 1,000 is not a good number. Let me say initially the pool was 1,400, and then the interest payments, having recovered the principal, it's 100, so you have 1,500. So it means that the growth rate is 100 divided by 1,500 positive. So when you work that comes down to about 1 divided by, I think, 15, and then you get the value for that in decimals. So it's plus that value. So it means that the pool has grown that much. When another person maybe takes from the market and then repays, maybe this time the 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 repayment takes the value up to 2,000. The 500 divided by 2,000, no, sorry, 500 divided by what, I think, is that the change or the previous one? Yeah. So 500 divided by the previous value, not the new value. Sorry. 500 divided by the previous value is the change. So you see that 500 divided by 1.5, I think that's 33% growth. So you actually see that, yes, the market has actually grown by so and so amount. So the first one should be 1 over 14, not 1 over 15. Kind of messed up the math there. But yeah, so as you can see, every time someone borrows and they make a repayment, the total value in the pool increases. Now, the only thing that can make the total value of the pool, that's loan book plus cash in hand, decrease is if there is a bad loan that we don't catch. But because of the way we are going to set up the loan package, we are liquidating the loan far before the loan becomes risky. So there will almost never be a scenario where the loans actually become bad because we're going to be running a bot that is constantly checking, and then the moment it sees there's a small deviation from the liquidation price, it snags it and liquidates it. I think I talk about this in this document, but let's see if we get to it. Yeah, it's there. It's at the bottom. Okay. So based on that, the underlying assumption is the accrued interest is always positive and always growing. So when a person deposits into the pool, we kind of track what the accrued interest is at the time when they deposit. And then the next time they want to perform an action, maybe as a lender, we track what the accrued deposit is at that future time. We deduct the difference between the current minus the initial time, which gives us the change in accrued interest. And then we then multiply that by the number of shares that they have so that we know how much they are due. We store that and then we then process their request. It's something called the pattern in programming called lazy updates. Um, you're going to see it live and direct. It's not as interesting as I make it sound. But the reason why we do it is because we don't want to store we don't want a case where whenever the accrued interest for the market changes, we are then looping through all the users to try and update their accounts. No, we're not going to do that because that does not scale. If you're from a computer science background, you would know that that has a problem in terms of the complexity. It's called O of N. It's like the more users you have, the more operations you have to run. It does not scale. So we came up with a solution that whether you have 1 million users or 1 billion users, the number of updates will still be fixed. So that's why we adopted that approach. But you see it in practice. Now, withdrawal principle. I mentioned here that when a person deposits, shares are minted. Similarly, when they withdraw their principal, those shares that they earned, we calculate what they've accrued, we store it in a particular like memory location, and then we burn those shares so that they can claim that amount in USDT, and those shares are removed from circulation, which would help reduce the size of the pool or the pool distribution. Yeah. So borrowers deposit volatile assets if AVA acts as collateral. And yeah, so the borrowers deposit the collateral and they accept the terms of the market. So the terms of the market are things like the liquidation threshold, the loan to value, the base interest rate per second. They might actually accept an interest rate, not a base interest rate, because we might make this something like base interest rate plus like K, where K is something that we mess around with based on like utilization or something. But I mean, it's just a thought that I'm having. Usually, I don't want to make things too complex. I like adding complexity after you've done like the basic stuff, you know. So that's that. That's for borrowers. Now, once a borrower has deposited, so they do one action, they deposit, then they can borrow up to the LTV, which is the loan to value, which is this value. This value, I'm going to talk about this very shortly. And then the repay loan, obviously, you kind of have to repay that loan. So yeah. So the market, the platform itself can do certain things. The platform can set interest rates. If you come here, these are some of the platform functions that I wrote. If you watch a video, you see them. These are empty functions, as you can see. There's nothing in them yet. But this just lets you know what the input should look like and what the output should look like. This is usually the first phase when you're doing like a development exercise. You need to map out your inputs and your outputs and what your functions should look like. So, yeah, the platform can set all these values. The platform can also adjust the reserve factor. So the reserve factor is something that I added. It's like the when a liquidation happens, the treasury, which is the person who's hosting the platform, can keep some of the funds from liquidation. I think I set it at 40%. They can keep 40%, 10% gets sent for insurance in case of a bad debt that happens. Um, 10%, I think, gets sent to the liquidator, the person who liquidated the loan, and I think 40% gets sent to the market. So it boosts the market share value. Yeah, and the administration can also trigger liquidation for under collateralized positions. So I said the platform is the one who does this, but the reality is anyone can, because if you look here, where the function I write liquidate loan, anyone can pass in a loan ID, provided you know what the loan ID is. Just pass it in and liquidate it. If it works, if the loan can be liquidated, you will notice this returns a boolean. Let me zoom in. This returns a boolean. If the loan can be liquidated, that means if this is true, this will work. If this is false, this will fail. So these two, they are kind of very linked. And I make this external because some people sometimes would keep calling this function until they find true. And then once they find true, they instantly call this. Um, that's one way of doing it. Yeah. So the contract architecture, I hope I can zoom in this thing. Okay, let's look at it. Let me, boom. Can I zoom in? Boom, 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 boom. Okay, first of all, let's get this popping. Let's blow it up. Okay. All right. This, you are going to, yeah, you all have access to this, so you can click on it, while I'm talking. Let me try and, okay, all right, cool. So here is this is as good as it gets, I think. I can't make it bigger. Oh, can I? Oh, I can. All right. So let me see if I can zoom. Oh, okay, now so far it's fine. So here we have our parties. We have our lender, we have our borrower, we have our liquidator, we have admin. These two can be the same or different, like I previously said. So the structure that we are taking is we're using something called the router pattern. Now, the router pattern it's like for those who like were born in Nigeria and like way back then, we used to have something called NITEL, where sometimes if you wanted to make some international calls, you would ring up like NITEL, and NITEL would then connect you to international call. I think obviously when phones became digital, like actual landline phones became digital, they started connecting you almost directly, But initially, previously, you would call and then they would link you to they would dial the international call and then they would like do some kind of connection. That's what this router is essentially. So the router is a messenger contract. Um, it sits behind all of these contracts and it's kind of like separates the complexity so that all the users don't have to be interacting with all these individual contracts. It can get very messy because it also exposes your contracts to a lot of vulnerability because someone could try and attack here, and attack here. It increases the surface area of the attack, basically. But by using a router contract, you kind of reduce the surface area of the attack. You make it such that everyone calls from one place. So if you are able to provide security on this router contract, you are going to see that you've kind of kept everything here safe. So this becomes like the bouncer, and this is like the club, and everyone there is chilling. All right. So when a user calls deposit or withdraw, they specify like a market ID. The market ID gets passed into this router contract, and the router contract looks up the contract address that owns that market ID and says, "Oh, it's this market's contract," and then it routes the request to here. So when you do a deposit, you actually do a deposit to the router contract, and immediately the router contract does that same deposit to this. Now, someone might say, "Oh, why can't I just like do a deposit to this directly?" You can't because this is blocking you. And you can if you give an approval to this contract, this one is not going to be able to take your deposit. So, and you can't talk to this directly. You have to go through him. So you have to give an approval to this contract, deposit the funds here, and then this contract immediately within the same call deposits it here. You can do that. It's not a big deal. I think I've also shown how to do that within this course, like within I think the third or second video. I think I did that. I definitely did something like that. Um, it may have just been approve and deposit, but adding one more transfer from is nothing fancy. It's just like putting like a withdraw, but you're withdrawing to this, or a transfer to. Yes, I remember I did do a video on that. So yeah, so you do a transfer to. So this is a contract to contract call. This is a user to contract call, and this is a contract to contract call. But this is happening internally, so you don't have to do anything because it will be coded. Now, I said the market contract is are clones of each other. So this is clone one, clone two, and clone three. And that means that all the market contracts have the same shape. What does that mean? All the market contracts look like this. Like everything that they have, they all have the same interface. So if I come here, this is an interface. They all have these features. And I extended a bit more features within the main contract, but all the market contracts, whether low risk, medium risk, or high risk, they all have the same. It's kind of like how all if you drive a Toyota, I don't know what they call them these days, Mozu. And that Toyota Mozu that you have, for every other Toyota Mozu that came out that year, they are clones of each other. The only difference is the vehicle identification number. So similarly here, all the contracts are clones of each other. The only differences are one, the contract addresses are obviously different. Two, the storage values, like the liquidation thresholds, are different. So for some, it's maybe 80%. For some, maybe it's like 40, it's like 650 or 60. I think the least we want to support is 60. So I think we're doing 60. I think we're doing 75 or 60. I think 70, and I think we're doing 80 or 85 or something really high. Yeah. So depending on the risk level of the market. So they will all have different liquidation thresholds. Similarly, their loan to value are also different. We're going to decide what this is at like when we are finished coding the contracts. It's not important what it should be at this point because they are all clones of each other. The point being that once you've done it for one, you've kind of done it for all. Actually, you have done it for all. You're just going to initialize the state with a different thing. So I think one thing that I would like to do is also make it initializable. Let me see if I can make that on the call. Bum, bum, bum. Accounts, utils, proxy, clones, initializable. Okay, boom. Let me see. I'm going to import this initializable. Hey, what was it just now? Okay. I'm going to import this initializable. This was actually not in the video, but I mean, you're here right now, so from this, we're going to do open Zeppelin contracts. I think contracts proxy, and then we are going to do utils, and we're going to do initializable. Did I not spell it well? Proxy utils initializable. So it's in utils, but it's Beacon Pro. Okay, I think I'm going to do this off. I'm going to do this maybe off chain. When I'm not recording and I'm going to debug it. I don't want to waste time trying to debug it. So we're going to make this initializable. What's an initializable contract? It's basically like a contract. So it's a contract that doesn't have a constructor, but it has a special function called initialize. So all clone contracts have to be, you can only clone contracts that are initializable. And the reason is because um, when you cloning, you are actually cloning the logic, but you are leaving the storage behind. So what the initializable is doing is it's separating the storage and the logic so that you can reuse the logic. But if you try to clone a contract that has a constructor, it's going to essentially going to copy the state of the contract, which is not what you want. You want the state and the logic to be different. So that's why we use initializable anyway. I'm going to add it in by the end of this video, and I'll push a commit to GitHub. Meanwhile, I've invited you all to this repo. So if you check your email, you're gonna see that you've been invited. So you can actually start making comments, contributions, anything you like. Yeah. So yeah, I've mentioned that the markets are clones of each other. So we are not going to focus on anything. We're just going to focus on the general pattern. Once the general pattern is fixed, we'll make it initializable and we'll be able to clone it. And I'll show you how to do the clone. The clone is happening at this router level. The router is the one that clones it because the router will be the one deploying all these contracts for us. So when we want to launch a new market, we call create new market within the router contract. It will deploy this one with the variables that we feed it, or deploy this or deploy that. That's another benefit of having a router contract. Okay, now this market contract, it has some components. It has a vault component, which is the one that allows it to mint and burn shares. It has an Oracle component, which allows it to get the price of an asset. So think about this. Let me say I want to I want to like borrow, yeah. So when I want to borrow, I pass in the collateral token address that I am using to borrow. Actually, I should actually add something here. 1 second. That should be under loans. I'm going to add a mapping. So this is a mapping of address to bytes, address to bytes 32, and I call it collateral address to price feed ID. So basically, the idea here is when a person wants to borrow and they provide the collateral address, I use the collateral address to get the price feed ID, And once I get the price feed ID, I then use the price feed ID to get the price. You might say, what's a price feed? It's in the video, but I'm just going to show you here again. This is what we're getting our prices from. So price feed ID, let's look at maybe a popular asset like, let's see, Bitcoin. Yeah. So this is Bitcoin. This service provides the price of Bitcoin aggregated from several sources. They give you like a confidence level, and so you can use this within your loan. This is a price feed ID. I think, yes. Valid, yeah, this is just information. This is the price feed ID. So when you get the collateral token address, you substitute it for the price feed ID, and then use the price feed ID to get the current price. And then once you get the current price, you are able to say, oh yeah, this is the current value of, so you're able to calculate price times quantity and say, okay, this is the current value of, actually, you don't even, this function might not be needed. Once you know the current price, you can say, okay, yeah, um, you're trying to borrow, maybe the loan to value is 50%. So 50% of this means that you can only borrow, so maybe you have one Bitcoin. Oh yeah, you do need it. So price times quantity, so you calculate it, and then you say, okay, 50% of price times quantity, that's 60, 155, basically. Is it 115? 110. Yeah, yeah, something like 55. So you can borrow up to 55,000 US dollars. So this returns what a person can. So this returns price times quantity, and then we'll take this value and pass it into something like that checks the loan to value ratio for that asset, and then we'll return the maximum borrowable amount, for that asset. Maybe I should actually write that function and just add it in here. Function maximum borrowable amount. Um, I don't know yet what I'll be taking. Maximum borrowable amount. I don't know yet what parameters I'll be taking, to be decided. A lot of all these things are to be decided based on, what we deem to be the right thing. So at that point in time, the Oracle will give us the price, and then we can use the price to know what the maximum borrowable amount is, and then the person can borrow up to that value, but not more than. And that's why we need the Oracle. Boom. So we're going to be calling the Oracle kind of like externally. Um, so we'll be using like an interface to call it. But this one, the 4626, we're going to make our contract a type of 4626. So we're going to actually inherit this eventually. That's the plan, so that we can have access to the features of this. So, but for this one, we're just going to call it externally, and then similarly, we also use an external DEX. I showed this on the call. This is what a DEX looks like. A DEX is a decentralized exchange. It's just a fancy name for That's what the decentralized exchange DEX. What does a DEX do? A DEX allows you to swap between two assets. So you can provide USDC, and we have 200. It will tell you, oh, you get this amount. Or you have 200 ETH, or you have this amount in ETH, you get 200 USDC. As you can see, you can swap back and forth, and then it charges you obviously some amount of money. The importance of this, I'm sure many of you already have figured it out by now, is that when we liquidate a person's loan, so because the loan is a volatile asset, maybe like ETH, when you sell it, you're going to get the payout in USDC. But how do you sell it? We're obviously not going to build the platform that does the selling. We're not going to do that because that would be insane. It's like you're building everything from the ground up. So what we're just going to do is we're going to use this platform, but we're going to use an interface that they provide, and we'll call that interface. We'll pass in all the values like, oh, basically sell my ETH, for of this amount, and then get this amount in 200, this amount of USDC, and then divide this amount between all the relevant parties. So this is how we end up liquidating a loan. This is what we do, because when you liquidate a loan, you are selling the volatile assets to get the stable asset. Since we've been on this call, I'm sure you've seen the price of ETH move. Yeah, see, it's never static, it's always moving. But this generally doesn't move as much. So yeah, we're going to be using that. So that's the external DEX. So I mentioned that obviously when we get some proceeds from liquidation, we pay the treasury, we put 10% in an insurance fund, then we also pay the vault, and yeah, pretty much it. So that's our contract architecture. It looks convoluted, but it really isn't. So I said here that all interactions flow through the router as a single entry point. So think of the router as a single entry point, basically. If you're going to interact with any of these markets, you make your order here, and then he goes to the kitchen and then delivers it to the chef, like creates whatever. So the router forwards the call based on risk level. The market contracts interact with the 4626 vault for share management. You can read up on this if you're interested. I actually recommend that you should. Um, Liquidations are handled through the DEX interface, like I said earlier, an interface of this. Price data flows from Oracle to both markets and DEX interface. Yep, we're using this for our Oracle, and liquidations proceeds are distributed here. So as you can see, by completing this project, you would have created a protocol that is interacting with two other existing protocols, which is kind of like a big deal. You know, most like regular new beginner devs can't even do that. They can only write a contract where they control everything. But this is like mid-tier stuff, right? So, contract interactions, I've said this many times, I'm not going to flog the horse. You can go through this: lender flow, borrower flow, liquidator flow, boom, done. Development roadmap. We identify all components and their relationships. We have done that. We designed the interface and specified the input and output parameters. We have also done that. Implement interfaces. Yes, we have also done that as well. And then I should have added a 3B here, which is define your storage layout. But I think I might add that in another comment. And then core development, begin the coding. So you see, we're just about to get to step 4. Now, for step 5, we'll be doing unit testing. I mentioned previously that Hardhat has a new version called Hardhat 3. I wasn't going to use it before, but I realized that it might be beneficial for you if I do. So I decided to use it. And the reason is because with Hardhat 3, you can write your unit tests in Solidity. So this is a language that you might already be somewhat familiar with. So it makes sense for me to just continue to use it. Now, obviously, our end-to-end test, we can't write it here. We need to write it in TypeScript. And I'm going to show you how to do that. So, well, at unit test, you want to catch bugs quickly. So as soon as you're writing the function, you're testing on the side. Integrate external dependencies. Now, this is what you do after all your functions are behaving as expected. So at the initial start, we are going to create an oracle, but the oracle we're going to create is a fake one. It's one where we provide the price of the asset, and then we try to see what the behavior would look like under different conditions. So say for instance, we wanted to check what the loan to value would be like if the price was this. We'll write that price in, we'll pass it in and check the behavior. Or want to see what the liquidation is going to be like. We would pass in a price that qualified for liquidation and see if it gets liquidated. So this is how you test your code. And then when you see that everything passes, then and only then do you then swap out your Oracle with something external, that so that way you can be sure that all your core logic is fine. Now, end-to-end testing, obviously this is going to be done in TypeScript. This verifies that everything is acting as expected. And then event review, here, if you notice, I have not added any events here because I intend to add the event after. Why? Because we're going to do something, we're going to create a subgraph. If you watch the video, I kind of show you what the subgraph is and what a subgraph does. Well, I'm just going to touch briefly on it. Basically, a subgraph consumes your events in the order that they happen and allows you to be able to run analytics on your contract. So it's very important. We use it at my previous company, TradeStar, and it allows us to see kind of like everything happening on the platform. So yeah, so these 8, 9, 8 to 11 are very linked to each other. You have to deploy to a testnet in order for you to use a subgraph. And then also the right SDK. By the time we get here, I'm hoping that you are somewhat comfortable with TypeScript, because I'll be writing kind of like a TypeScript interface of which is like a TypeScript copy of the smart contract so that a front end can talk to it as well as a back end. Um, I'm really hoping that you guys find this easy, because TypeScript, this course is not a TypeScript course. So I would probably go hard and go fast on this because, of the time that we're working out, trying to be time sensitive. But I will hope that you can usually when I'm trying to learn something, I always write the simplest function possible. So you can write like an SDK for like a counter contract. So basically to have something small like increment, decrement, and then you can see how it works. Then you can use that to build your understanding of bigger things. That's literally how I learned it. So audit preparation. Typically, you can't take a product to live without doing audit checks. Um, We're not going to be doing that because we're not auditors. Auditors subjected to some checks. One of those checks is like they'll run something like Slither on it, which I just ran. And Slither is going to is a static Slither is a static analyzer and it checks for vulnerabilities. Or you can just inherit there's like a repo you can inherit and to run all the tests for you. For some weird reason, the splitter is not running. Oh, I didn't run it. No, not found. I guess I have not installed it on the system. We'll see. Let me check. Nope. I haven't installed it. And then you deploy, and then that brings this bit to an end. So yeah, just spend the last 1 hour going over this doc and talking through it. I'm going to spend the next maybe 10 minutes, 10 to 15 minutes going through this as fast as I can. And then I'll use the last 15 minutes to take your questions. Okay. So the contract has several parts. We have the global states. The global states are things that affect everyone. Things like liquidation threshold, loan to value, base interest rate per second. The loan state can either be active, repaid, or liquidated. Um, so a loan doesn't exist, but if a loan exists, it's always in one of these three states. So we created a struct for a loan, and each loan should have obviously the token that you're using to borrow and the amounts that you've deposited, and it should also have like the price feed ID, which is why we created this mapping. So we can use this mapping to get the price feed ID, so that when someone is trying to liquidate and then they get the price feed ID, they should also be able to do a mapping of bytes 32 to what's it called? Address public, which is price. Actually, this is not necessary. I just clocked. This is not necessary. Why? Because if you have collateral token address, you can just use it to look up the price feed ID, you know. So one might debate and say it might be pointless to have this, but I think I'm going to leave it there because there might be a need for it. If it turns out there's no need for it, we'll take it out. Because now that this mapping, previously when I wrote this mapping didn't exist, but now it does exist. So technically it's made this kind of redundant, but we'll see. Every loan has a liquidation price, as you know, which we'll calculate at the time when we're creating the loan. And the amount borrowed, we also know this. Why? Because when you're trying to liquidate this loan, so a person can deposit maybe 1,000, maybe $1,000 worth of Bitcoin, but they might decide to maybe borrow only 500. So like they might decide to say, okay, I have a Bitcoin is not a good example. Just assume that there is a volatile asset that um the quantity of it is 1,000 when you deposit it, but you only want to use 500 for this particular loan ID, so that you can use maybe 400 for another loan ID or 300 for another loan ID, that sort of thing. So you will know the total amount deposited. You will know, so this is the amount that when a liquidator liquidates the loan, this is the amount that they get, 10% of this. And then when the person repays, this is the amount that they're repaying. Interest rates, obvious for obvious reasons, because when they're doing the repayments, you need to be able to calculate, oh, amount borrowed times interest times time, and is this repayment amount valid, true or false? And then if the loan state is active, we know. Prepaid, we know. Liquidated, we know. There's a mapping of bytes 32 to loan. This is just a loan ID. Okay. Loan ID to loan, nothing fancy. And this is the mapping of address to price feed ID. You know, this is a mapping of lender state. So for the lender, when you deposit, this just shows you the balance, and then this shows your last reward checkpoint at the time of interaction. I'm going to explain what this means when we're doing the accrual calculation. It will make sense then. And whatever rewards you have generated by the time you're interacting with the contract, it's stores it here. When you're depositing for the very first time, this will obviously be zero. But when time has passed so like I said, when you deposit for the first time, this is zero. The last reward checkpoint will be the global accrued interest rate at that particular time. Maybe what that value will be, we're going to store it here. So the next time you're interacting with it, it's going to check global, and then it's going to compute that current value minus this value multiplied by the amount of shares that you have. Speaking of amount of shares, I haven't added it here. And I'm going to add it once I inherit 4626. So the amount of shares, actually, and just add it here. U into 56. amount in shares. Yeah. So you calculate the difference between that multiplied by the amount in shares, and that gives you the pending rewards on your store. As you can see that I'm actually building this stuff on the fly. So as you're thinking through it, things come to you. Oh, I need this. Oh, I need that. And yeah, this is a mapping of the address to lender info. So yeah, you can borrow, yeah, you can deposit, you can claim. This is the borrower state. The borrower state is a mapping of the borrower address to the borrower account. The borrower account has a mapping inside. I'm sure you've never seen this before, this setup where a mapping is inside the struct. It's possible to do that. The reason why we do this is we can actually have a nested mapping, but I think it's cleaner this way so that it doesn't look too convoluted. It's because someone might deposit Bitcoin, some amount of Bitcoin. They might also deposit, same person might also deposit Ethereum some amount or Doge some amount. So you see, there are multiple assets a person can have with multiple amounts. So whenever they want to borrow, they will be borrowing from one of these assets, which is why if you look at borrow, it takes in collateral, address, and amount because you'll be decrementing from this whenever you are doing like a proper borrow. So you decrement from this, which means that the amount borrowed would increment and this would not change, obviously. This only changes on deposit. And then if there's a withdrawal, this also changes as well. So yeah, that's that. Active loan count. I was on the fence about this, whether to add this or not. But I thought, hmm, maybe I leave it there and see what I can use it for. Liquidated loan count. Oh yeah, I remember the reason why I added it. The reason is because as this platform becomes like gains more traction, some people are going to have an active loan count that is high with a low liquidation loan count. Some people are going to have a high liquidation loan count and low, maybe possibly even higher than this. So this allows you to actually estimate like credit worthiness. Now, obviously, you don't estimate credit worthiness on chain, you do it off chain because that's the best way to do it. You can use a machine learning model to do that. There is a machine learning model that does that. If I recall correctly, let me check. It's called a binary tree. Decision tree. Yeah, a decision tree. Yeah. So you can host that service and call it, and then it gives you that. But I mean, that's future stuff. Yeah. So um these are the lender functions: deposit, claim, withdraw, borrower functions: deposit, loan collateral, borrow, repay loan, and these are the platform features. Yeah, so that's pretty much where we at. I'm going to start. The first point of business will be for me to write these lender functions. Once this is done, I would then write these ones, and then I would then write these ones. I'm sure looking at all this, I'm sure that you guys can actually write this function. You don't need my help to do that. But if anyone wants to take a shot or try, obviously you know the steps. Create a PR, try and write it. It's so basic. Basically, it's just set a value and check that the value is not zero or the value is greater than some constant or something, whatever. So all these are platform functions. Yes, I've been talking for the last 1 hour and 6 minutes. I would like to stop sharing my screen. 1 second. I'm going to also stop the recording so I can take your questions. Boom.